be here today. He's sick. He did assure me he'd be watching from home. So we can say hello, Jordan.
Hi, Jordan.
Hi, Jordan. We all miss you. Okay. Okay, so we're in chapter 13. We're about to finish our work with it. We and we kind of got halfway through the final lemma yesterday. So I don't just want to pick up immediately from there. So I just want to bring people back up to speed. Okay. So we're trying to prove the fundamental theorem of finite abelian groups. So I'll do it quickly. I won't do. And this says every G, which is a finite abelian group, can be written as being isomorphic to a direct product of various cyclic groups, and they all have prime power order. So this is some prime to some power, some prime to some power, some prime to some power. The direct product of cyclic groups, all of prime power order. These primes are not necessarily pi primes, but not necessarily distinct. Okay, so it's not like the primes occurring when you write the prime factorization of an integer, where you separate all the primes into prime powers and each way is different. Here we could, some of these primes could be repetitions. So that's the task of the whole chapter, improving this result. To get there, so the first time a direct product appears is in lemma 13.8. But the preparatory lemmas for that is saying that if you have any group, finite abelian group, any prime number dividing the order of the group, lemma 13.6 says there are elements in G of order P. There are some elements around there that have that order. That gives us the definition, or that prompts us then to make this definition of a P group. So a P group is one which all of whose elements are powers of some particular fixed prime P. You could talk about a 5 group, 7. So G of P group is for all x and G, there exists a K such that the order of the x is P to that power of some power. So lemma 13.8 then, and what lemma 13.7 says is that, well, that collection, that group, the size of that group will be a power of P as well. So every element has order some power of P, and the size of the group is itself some power of P. 13.8 then is where we make our first significant step towards this. Is in 13.8 we write G not like that, but G as a direct product of these groups, G sub 1 up to G sub whatever. Okay, let's go K here, but it's not necessarily the same K's up there. So this is an internal direct product of the subgroups GI. The subgroups GI, you've got one for every prime PI appearing in the prime factorization of N, which is the size of them. Okay, so G is a finite abelian group. These GIs are called the primary components. Primary components. You've one for each prime dividing the size of G. Okay. So these are not yet these groups that we want to see, okay, but it gives a direct product, internal direct product representation of G as a product of these groups. Okay, each of them is a P group. GI is the set of all the elements from G whose order is some power of the prime P. You gather together all the elements which have order power of P1, you gather together all the elements which have order power of P2, and so on and so on. Okay, for each prime PI dividing the size of G. So this gives us a clear path to this result. The path to this result is to show that each of these GIs is isomorphic to, can be written as a direct product of groups like this. PI some power. PI some power. Okay? So that each of these GIs can be written as a direct product of things appearing like that. And so then when you string them all together, you'll just have some big, giant direct product. Okay. So what we're missing is the last thing to prove is this result, that a P group, you've got various P groups here for various primes, and the various primes dividing the size of G. Is to prove that a P group can be written as a direct product of these cyclic groups of prime power. Okay, this is the job done by theorem 13.9, okay, which we started proving yesterday. So for theorem 3.9, here we let G be a finite abelian P group. So you think of it as being one of these GIs. Okay. So G is not a general finite abelian group, but a finite abelian P group for some prime P. The lemma 13.7 said the size of G will be some power of P, P to the power of some P. And what the result says is, it doesn't establish that it can be written as a big, long direct product like this, but it just says that you can peel off one factor in a direct product, which is a cyclic group of prime power order. And that you can write this G as being isomorphic as an internal direct product of a cyclic group. And this G is coming from G, so it will have order some power. It will be a cyclic group of prime power order. It will be one of these Z's up here. Internal direct product with H, where H is some other subgroup of G. So this lemma, the work that this lemma does is it takes one of these GIs and it says, well, you can write the GI as one of those ZPs that we want. Direct product with another subgroup of GI. That other subgroup will again be a P group, again be a PI group. There's all the elements in it, there'll be elements from GIs, they'll all have order some power of PI. So there's nothing stopping you from applying lemma 13.9 again to that other factor H and splitting another cyclic group off the requirement. So keep on applying 13.9, keep on peeling off these cyclic factors in the direct product until eventually you've got this GI written all the way like one of these. So it's kind of like an induction process. Okay. Okay, so where did we get yesterday? So I won't go through the detailed arguments that we did yesterday. I'll just give a summary of where we got to. So I'll just switch to the visualizer now. Any questions so far on the overall sketch of what's happening? Okay. In lemma 13.9, this is the proof and the story so far. Just put down what we've established before is we pick out an element little g from G such that G has maximal order. Order of G is some power of P. What do we call it? We called it P to the N. Okay. So this, you pick out one of the elements that has maximal order. Okay? So every other element in G has order less than or equal. Now every element has order some power of P. It's a P group. Every element in G has order some maybe smaller power of P to the A, where A is less than or equal to M. So G is maximum. Now, if G was not equal to the cyclic subgroup generated by G, and if it was, we would just stop because there'd be nothing more to prove. Because we would have proved that that primary component was just a single cyclic group. So if on the other hand G is equal to that, then the lemma has been proved. no extra work to do. But if G is not equal to that, then there are other elements around. Then we let H be an element of the complement G less, i.e. H is not an element of cyclic subgroup generated by G, but not just any old element, one with minimal order. So you're a minimax, sorry. Such that order of H is minimal amongst elements, all elements in complement of cyclic subgroup generated by little g. Okay? There's a mixture of minimax. At the start, out of the group G, we pick an element with maximal order, which generates a cyclic subgroup of maximum size within G. The size of that we know will be some power of the prime P. G is a P group. Every element is that kind of order. It might be the whole of G. If it is, we stop. Nothing more to prove, just G is a cyclic group of that size. But if it's not the whole of G, then so there are some elements outside of cyclic subgroup generated by little g. We choose one, H, which has smallest order of all such elements. We then showed two things. This is the work we were doing yesterday, and some quite detailed arguments. But we showed that the order of little h, which happens to be the same as the order of the cyclic subgroup generated by H, that this was equal to P. Not some higher power. Remember, every element in G has order some power of P, but that this element had order as small as possible. We know, of course, that little h is definitely a non-identity element because we're saying it's not in a subgroup. So it certainly can't be the identity. So H cannot have order 1, so it's a non-identity element. But it has the smallest possible order out of all that it could have within G. It's one of these elements of order P. And secondly, we showed that so we let capital H denote the cyclic subgroup generated by little h. We then showed that the intersection between the cyclic subgroup generated by G and the cyclic subgroup generated by little h, that is trivial, as small as possible. That only contains the identity element. Okay. That was the stage we got to yesterday. So that's just a recap to bring us to the stage where we were yesterday afternoon. Okay. Now, so what can you say here? I mean, remember, we're in an abelian group, so there are no other conditions necessary to check for the existence of eternal direct products. So we know now that the product of these two, cyclic subgroup generated by G and the cyclic subgroup generated by little h, just the setwise product of them will be a subgroup. And it will be an internal direct product. It will be isomorphic to the direct product of these two. We can't expect that to be the whole of G. Because otherwise we'd have ended up showing that every finite abelian P group is the direct product of two cyclic groups, one of order P and the other of order some power of P, but that certainly isn't the case, because you can think of examples like Z2 plus Z2 plus Z2 plus Z2. It could be a direct product of any number of cyclic groups of prime power orders. So we certainly should be able to show this is just the direct product of two. So we don't expect the direct product of cyclic subgroup generated by G and cyclic subgroup generated by little h. We don't expect that direct product to be the whole of G. What we do, we are going to get something out of it. Oh, I should have said that that the whole thing was proof by induction. Proof by induction on n, where n is the size of G is P to the power n. G is a P group, So the previous lemmas say that the order of G is some power of P. So G is order some power of P, and we're going to do this proof by induction on N. And the base case when N, okay, don't go over details of this way too much. So the base case was when N equals 1, but then the order of G is just P, so that means G is just the cyclic group of order. G is just the isomorphic to cyclic group of size P, and there's nothing else. So there's nothing else to prove. So the induction, so, but that's the base case, N equals 1. So the induction assumption will be we assume the lemma is true for all such groups, finite abelian P groups, all such groups of order P to the K, where 1 is less than or equal to K, and this is strictly less than N. So we're assuming it's true that the lemma is true for all P groups of smaller size. That is, any P group of smaller size will factor will factor as cyclic subgroup generated by G cross H cross some other subgroup. So we have not used the induction assumption yet. But we're going to have to, because we're carrying out an induction proof. So the way we do it is, well, you see, we're stuck with this group G, which is size P to the N. And we've assumed something true about every smaller. So the way to do it is to make use of the fact that we've isolated out this subgroup of size P, subgroup H. Right? The element little h is order P, so the cyclic subgroup generated by it has size P. And this gives us the ability to pass to the factor group, quotient group is called by other authors, pass to the factor group GH. Now, just some first immediate observations about the factor group GH. First of all, note that the factor group is a P group. This kind of needs a little lemma by itself almost. And is everybody happy with this? So remember, a P group is one where all the elements have order some power of prime P. Now that is true for G. Is it true of the factor group G mod H? Well, remember the canonical homomorphism phi going from a group to its factor group. That sent an element G to the coset, G times H. Yeah? The way you map, that's the homomorphism from any group to a factor group. This is a homomorphism. So if the order of G is P to the A, then what happens when you raise phi of G to the power of P to the A? I'm investigating the order of phi of G. I'm going to show that it has to be some power of P as well. What happens when you raise phi of G to P to the A? Well, because it's a homomorphism, that exponent side. Yeah. So it's phi of G to the power of P to the A. That's justified because phi is a homomorphism. But that's phi of E, as we've just said. G is order P to the A. So that means it's E, the identity in the factor group. So here we have the element 5g raised to the power p of a, it gives you the identity. So that implies that the order of 5g divides pa. Okay. If you raise an element to some power and you get the identity, that means you know the order of that element. The smallest such power you could raise it to get the identity is a factor of that exponent. Could be all of it, but it must divide that factor. If you raise an element to a power, remember you're going round and round the cyclic subgroup generated by that element. And if you go round and round, and if you find you end at the identity, that means you must have gone around the full cycle some whole number of times. And so that means that the total number of steps you've made, which is p to the a here, must be a multiple of the minimal size of the cycle, which is the order of the element level g. Well, what kind of divisors does p to the a have? I.e. is equal to some smaller power of b. Smaller power of b. But b is less or equal to a. So every element in the factor group has order a power of p. So the factor group is a p. It's a p group. Agreed? That closes that bracket, that little beer back clean. So G mod H is a p group. What size does it have? Size of G mod H. So how big is a factor group of a finite group?
Size of G divided by the size of H.
Yeah, size of G divided by the size of H. The number of cosets. Yeah. Exactly. Called the index. The index of H and G. Yeah. All these kind of multiple names for the same thing. So what is that? Well, you see, G was a p group. So G has size some power of p, you know? H we've already declared has size p. So it has size p to the n minus 1. In other words, emphasize this, i.e. it's covered by what? Important step in our argument that we make, it's covered by the induction assumption. We've assumed, see, we're in the middle of the proof by induction. We've assumed that the lemma is true for all groups of order p to the k, where k is strictly less than all groups of size, all such groups, finite abelian p groups of size less than the size of g. So the factor group is certainly one of those. So it's covered by the induction assumption above. Brilliant. So we can extract out of applying the lemma to G mod H, we'll be able to lift it up and get the truth of the lemma for G. Okay? Because we always need, in a proof by induction, we always need to be able to link back somehow to the previous cases, to make use of that assumption and draw it forward to the case that we're trying to prove. So those are two important facts about G mod H. So okay, any issues? Okay, so consider our special element G. Remember, G has this maximal order. What did I call it? P to the n, maximal. All such elements of G. And what is the order of the element of the element represented by it, the coset represented by it in the factor group? What is that? Well, we're going to claim that the order it has is the same as the order of G. P to the n. We know, in general, we know about that whenever we have a homomorphism, image of an element divides the order of the element. Okay? So typically, when you apply a homomorphism, you send elements to elements with smaller order. Okay, it's your typical behavior of a homomorphism. But no bigger order. Smaller order, and it has to divide the order of the original element G, but in some cases it can be exactly equal to the element of the original order. In particular, when you got an isomorphism, maps any element across to an element with exactly the same order. Okay, so we're claiming here that there's no loss of order. The order of the coset represented by little g is still the same as the order that little g had. So we do this by a little proof by contradiction. If the order of GH is less than the order of G, i.e. the order of GH is less than or equal to P to the n minus 1. G had order P to the n. So if GH has order strictly less than that, remember everything is P groups here, factor groups of P groups. So the order an element can have is some power of P. So it's going to be smaller than P to the n, it has to be power of P to the n minus 1 or some smaller power. So what does that give us? That implies then that if you take this coset and raise it to the power of P to the n minus 1, we'll get the identity element, which is the coset H itself. But how does multiplication of cosets work? Well, you just perform, or how does exponentiation of cosets works? Well, it's the coset corresponding to this operation applied to the representative. Doing group operations with cosets, you just do them on the representative and look at the coset where that representative is. So this is the coset corresponding to g to the power n minus 1 times h. So this must be equal to h, the identity in the factor. But what does that tell you? That tells us that g to the power p to the m minus 1 must be an element of h. How can you have because when you've got a coset of h equal to h, that means the representative must be already in the coset. Basic fact about cosets. Basic fact about cosets. In general, xh equal to h, that implies x is an element of h. It's true all the time. Can g to the p m minus 1 be an h? Where else is this power of g? Where else does it naturally belong? Well, it naturally belongs in the cyclic subgroup generated by little g. So we're back to making statements. If we were making statements about the factor group, but never back to making statements in the original group G, about this element. So that implies that G to the P m minus 1, it's an element of the intersection of G with H. Well, previously we proved what? Previously we proved that these have trivial intersection, just equal to the identity. So that implies that G to the P to the m minus 1 equals the identity, and what do you make of that? That look right? Seems to contradict this statement here, that the order of G is P to the n. The order is the smallest exponent that gets you back to the identity. Here we seem to have found a smaller one. That's a contradiction. But what led to the contradiction? The thing that led to that contradiction was this supposition here. If the order of GH was strictly less than the order of G. Well, that can't happen. It can't be strictly less than, so it must be equal. And in general, for homomorphic images, must always have order less than or equal to the order of the image. So they can't have order strictly less than. The only other option is it's order equal to. So in fact, that was what led to the contradiction. So the order of GH is equal to the order of G, which is equal to the M. And what does that tell us? That tells us, therefore, GH also has, because remember, we're interested, what we're angling for is to apply the lemma to the factor group. So we've made the induction assumption that the lemma applies to all smaller groups. So this also has maximal order in G mod H. What do you find with that? Little g have maximal order in G, order P to the M. Basic fact about homomorphisms is when you pass to a homomorphic image, the order of things gets no bigger. The order of an element, the order of the image of an element under homomorphism, the order of the image divides the order of the original element. The orders can only get smaller when you pass to the factor group. So if little g had the biggest order possible in G, and the coset of little g has exactly the same order, but everything in the factor group G mod H has equal or smaller order than the order it had in G. So therefore, this coset must also be a biggest possible order, maximal order in the factor group. Okay. So that means by the induction assumption, the lemma applies, this lemma we're trying to prove applies to G mod H. So we can say G mod H is isomorphic to the cyclic subgroup generated by the coset G mod H, and a subgroup which I'll call curly H to distinguish it from the H that's already mentioned. Okay, so it's script handwriting H or so. Okay, so that's for some subgroup curly H of the factor group G mod H. So that's applying the lemma, because we've assumed, because we're in the middle of an induction proof, we've assumed the lemma applies to all smaller groups. So there it is, we've written it out. However, we can write this as the cyclic subgroup generated by GH with a quotient K mod H, where K is a subgroup of G containing this subgroup, capital H we've talked about. Now that comes from what we call the correspondence theorem. Which was 11.13. Now, that was a technical result which we proved at the time. I was in the isomorphisms chapter. The correspondence theorem referred to any time you look at factor groups. It said that, well, if you're looking at what goes on in G and you're looking at what goes on in the factor group G mod H, it said that there was a 1-1 correspondence here between subgroups of the factor group were in a bijective relationship, a 1-to-1 correspondence with subgroups of G containing H. So subgroups of the factor group, so this would be like our K, and the subgroups over here are themselves factor groups. So subgroups of the factor group are themselves factor groups of subgroups of the original group that contained H. Subgroup you're modeling out. So that was the correspondence theorem 11.13. And that's what allows us to drag back the conclusion we reached here about the factor group, to drag it back into something going on in G. So this K is the group we're looking for. Okay, so we need to establish a few things about K. So basically, K is the other subgroup we need. For us to be able to say that G is isomorphic to cyclic subgroup of G cross K. That's what the lemma claims, that there is this other subgroup of G, and that it's an internal direct product with a cyclic subgroup generated by the G. But now just the couple of last things we need to establish for that is that these two groups have trivial intersection. Remember, K is a slightly larger subgroup than H, subgroup containing H. Okay. Well, that's kind of clear-ish, is it? A little proof of that. If you had an element B in the intersection, that would imply that the coset BH was in the intersection between G and the intersection of the cyclic subgroup generated by the coset GH and function KH. As B appears in K, then the coset BH appears in this factor group. And if B appears in cyclic subgroup generated by G, then the coset BH will appear in cyclic subgroup generated by GH. But we've already proved, see the lemma, this came from applying the lemma to the factor group. So the intersection, so that's a direct product. So the intersection with those two is trivial, but that is just equal to the identity in the factor group, which is the group H. So again, that implies B is an element of H. But then B is in H, but it's also in cyclic subgroup generated by G. We know those two are trivial intersections. So that implies B is in the intersection of G and H. We know to be E, so that implies B is E. So that establishes that claim. Anything in the intersection is trivial. There's only the identity element. And last thing we need to claim is just that simply that G is the set-wise product of these two groups. That everything in G can be written as something from the cyclic subgroup generated by G multiplied by K. Finally. Then, as they have trivial intersection, this set-wise product is isomorphic to the direct product of the two. So that last final claim is, well, it's a little proof for that, would be let X be an element of G. And we want to prove that we can write it as something from this group multiplied by something from that group. Again, we have to pass to the factor group. We know that X times H, that coset, we already know that the factor group is isomorphic to this direct product. So any element of the factor group, namely this coset XH, will be something from here multiplied by something from here. So something from here, something from there looks like G to the H to some power R, multiplied by something from there, we'll write as a little k times H, or some little k in the group K. And remember, powers of a coset is just the coset corresponding to power of the representative. But now we want to say something about X. Now X is one of the elements in this coset. X times E, the identity element from the subgroup H. So X itself will be one of the elements from here. Now probably not the one corresponding to choosing the identity, but we can choose other elements. So there'll be some choice of a H1 and H2. A H1 times a K times a H2, and that will be for some little H1, little H2 coming from subgroup H. But what are we looking at overall there? Remember, K is a subgroup containing H. So this triple product here, H1K, H2, that can be said to be an element of K. Because subgroups are closed under multiplication. So the H1 and H2 belong to K. We're multiplying by some other element, little k. So this is certainly an element of K. And a power of R, of course, an element of the cyclic subgroup generated by G. So this, any element X from G can be written as a product of two elements, one from the cyclic subgroup generated by G and one from the subgroup K. Now it looks there like there might be ambiguity about which choice of elements, one from the other, you can choose, because there's this here, I just said this was for some H1 and H2 and for some K. But this thing we've shown up here already, that these things only intersect in the identity. That the consequences of that is that there's no ambiguity in the choice of elements here. There's a unique choice of element from the first group and a unique choice of element from the second group, such that X is the product of those two. But that's taken account for in the theory of internal direct products. This trivial intersection property, that means that there's no ambiguity about the representative. So that completes the induction step. So G can be written as per the lemma, i.e. G is isomorphic to the direct product G, so that's your cyclic subgroup of order some power of P, and the direct product with the subgroup K. So that completes the induction step. We assumed it was true for all smaller groups. Now we've shown it's true for groups of the next size, this G, which is size P to the n. So therefore, by the principle of induction, we can say it's true for all groups. It's true for finite abelian P groups, G of order P to the n, but now by induction, this tells us it's for all n. So true for all. Okay, so that finally completes the proof of lemma, which finally completes the proof of our fundamental theorem for finite abelian. There's a slight extension of the theorem mentioned then, which is theorem 13.10, which just extends it to denote, well, okay, that's for finite groups. What about infinite abelian groups? So the fundamental theorem of finite abelian groups says every finite abelian group is isomorphic to a direct product of something looking like that. If you then take in possibly infinite abelian groups, it's not as if there's some whole other wild kind of possibilities of structure you can have. There might be some finite part which is isomorphic to a direct product of cyclic groups like that, and then you just have some other number of factors in the direct product which are Z, the infinite. So the extension of it to infinite groups is the result doesn't look all that different. Okay? So any finite abelian group we can expect to be isomorphic to something like that. Direct product of infinite cyclic groups of prime power order. An infinite abelian group will always be isomorphic to something like this. There might be this torsion part, this part which contains elements of finite order. And then the infinite order part of it is represented by some number, some number of factors in the direct product which are copies of the infinite cyclic set. Okay? So it extends in a nice enough way to infinity. It's not as if something else wild and complicated happens when you're past the infinity. Okay. Okay, good. So in the tutorial I think I'll pick out, there's a whole other section here that's about solvable groups and that, which we won't be covering. But I'll look for, I think we've more or less covered all the exercises relevant to the material we've been doing from this chapter. I think I'll pick out some good representative problems from earlier chapters just to get us doing some more thinking about arguments and that. And anything you come across, any questions you might have? We looked briefly at one of the past exams last Friday as well. We can maybe start to do that as well. And we will be giving you some more another mock exam as well. Yeah, just some good work. So, right now.